Fine. Am I audible? Dear learners, greetings of the day. This session is a revision session as I have already completed the four sessions for doubt clearing. Uh, I, Shiva Singh, will try to cover up all the doubt clearing session in this one lecture and make sure that this will help you through the exam of this course. I will be starting now, and the recorded lecture will be available on the YouTube channel for future reference. Wait, fine, fine. Check. Okay. Fine, the slides are visible, I think. You can respond in the chat box whether my slides are visible or not. Fine, let's start. Uh, Good afternoon, everyone. My name is Shiva Singh. I am here for the revision session of Metal Mediated Synthesis 1. And this course is coordinated by Professor Devabrata Maiti at Department of Chemistry. And currently, I am enrolled as a PhD scholar at Polymers and Process Engineering Department, IIT Roorkee, and Department of Chemistry, IIT Roorkee, with Professor Pradeep Kumar Maji and Professor Kaushik Ghosh. And my PhD thesis is funded by Prime Minister's Research Fellowship Program. Fine. This session will cover the introduction and the solutions of the relevant problems, basics involving in it, and the explanations. So before starting this, I should introduce myself. My name is Shiva Singh, and I have a versatile profile right now. And currently, I am a PhD scholar at IIT Roorkee. Previously, I was a master's student at VNIT Nagpur, and before that, I had did my graduation at Department of Chemistry, Kirodimal College, Delhi University. During this journey, I have did various summer internships and projects. My research project was done with the Professor Chayan Das at VNIT Nagpur during my masters, and before that, I have did two summer internships with Professor Alakesh Bisai and Professor Akhilesh Kumar Verma. In the summer internship with Professor Akhilesh Kumar Verma, I have did this transition metal catalysis, like Shonogashira coupling, which I will be teaching right now, and synthesis of hydrogens, Wills-Merhack reactions, etc. During this journey, I have achieved few of the awards, like inspire from 2014 to 2019. I was also got selected for SN Bose scholar program in 2018. I have all cleared gate in 2020. I have inspired JRF in 2020, and currently I am working as a prime minister's research fellow, which have been started from 2020. So in this revision session, I will start from hydrogenation. Wilkinson catalyst is commonly employed in what reaction? As I have told in my first doubt clearing session, wherever Wilkinson catalyst is there, we have to just go for the hydrogenation. Fine. This is the structure of Wilkinson catalyst, and here is the cycle. Initially, the ligand dissociation occurs, and when vacancy is generated, in this vacancy, hydrogen comes, and it is oxidative addition and reversible reaction. Whenever hydrogen comes, the geometry of this changes to octahedral, and the ligand association occurs. Whenever ligand association occurs, and then 1,2 insertion happens. During this 1,2 insertion, these hydrogen come to the alkene moiety and reductive elimination occurs, and our alkene gets converted to alkane, and again the catalyst comes in the cycle and keep on repeating the cycle till either reactive material have been consumed, or the catalyst got quenched. Generally, the quenching of the catalyst happens due to the external presence of moisture or uh, impurities. For understanding the mechanism better, you can go through these research articles. Fine. The next question. In asymmetric hydrogenation reaction, the major enantioselective product result from minor substrate, catalyst diastereomer, minor enantiomer in substrate, major substrate, catalyst diastereomer, major enantiomer in substrate. As I have discussed this situation. Suppose this is our catalyst and this is our substrate. Fine. So whenever there are two possibilities, either it can attack from re phase, which is this, or C phase, which is this. Fine. And if we see here, here hydrogenation occurs fast and here slow. Why? Whenever it comes from hindered side, slow, or 10% only diastereomer is formed, but in this case 90% have been formed. But as we see, 90% formation means a very stable product have been formed. So further, this migratory insertion becomes difficult. But in the case of unstable, which is 10% only, the migratory insertion becomes easy and reductive elimination occurs, and the product forms with the enantiomer axis of 95%. Only 5% of this product have been observed. So, if I explain with the book, the initial selective step is oxidative addition of hydrogen to the square planar. This step to the square planar diastereomic substrate complexes that are in the rapid dissociation equilibrium. This is the rapid dissociation equilibrium. Either this can be exist here or here, but generally this is the lowest and this is the highest. So the major enantiomer of the product arises from the minor substrate. This is minor substrate. Okay. It was shown from kinetic studies minor diastereomer is 580 fold more reactive towards hydrogen. Why it is like this? It is due to the instability of this substrate. Okay, I think it is now clear. I have to move to the next. Which of the following is the correct statement for the rate of the hydrogenation? So for this type of questions, you need to learn only these four concepts. Terminal alkynes are hydrogenated more rapidly. Then conjugated dienes are reduced more slowly than isolated. Why? Suppose I have this type of alkene, right? The bond will keep on conjugating here, here, and here, right? So whenever they are conjugating, there is more stability. So the interaction with the metal center will be difficult. So it will result reduced activity towards the metal and hydrogenation. Internal and branch alkynes undergo hydrogenation more slowly than terminal ones. So, substrate containing polar function groups, hydrogenation more rapidly than those having no such group. Whenever we have a polar group on an alkene, what it will do? It will pull the electrons towards it and create the instability. As I have told earlier, instability results in the more product formation. Fine. So let's move to the next question. The given catalyst is known as. This is the catalyst, and these are the options. Such questions are expected to come in the exam. And this is shock Osborne catalyst. You have to learn the structure of the catalysts. so that it will be easy to attempt the questions in the exam. Further, in a metal alkyl compound, which sigma bond R group could undergo beta hydrogen elimination? These are the options. And if we see here, this is ethyl group. This is ethyl group, metal, alpha, and beta. This is beta hydrogen. This hydrogen goes to metal, and this bond comes here, and such type of formation occurs. So here, beta hydride elimination is possible. But if you see here, alpha, beta position does not have any hydrogen, so there will not any possibility for the reductive elimination by a beta elimination. So if we see here, here also beta hydride elimination is absent, and here we can see beta hydride position is vacant. No beta hydride or beta position is there. Fine. The order of reactivity of alkyl halides toward oxidative addition. Whenever we go for oxidative addition, it is a process of add two anion ligands, suppose A and B, that are originally are part of AB, like H2 or M methyl iodide, onto a metal center. Suppose this is the metal center, and is so significant importance from the perspective of both synthesis and catalysis. The reactivity of alkyl halides towards oxidative addition to metal depends on the relative strength of Rx bond. The weaker the bond, so if you see here, carbon and iodine bigger in size, carbon smaller in size, so weak bonds. So this is the correct answer, and the answer comes from the strength of aryl or alkyl halide bonds. Fine. Singlet carbene has a pair of electron in sp2 orbital, one single electron in sp2 orbital, a pair of electron in sp3 orbital, a pair of. Now I will be discussing only carbenes in next 2 3 slides. A pair of electrons in sp orbital. The correct answer is a pair of electron in sp2 orbital. If we see here, this is the sp2 orbital. See, it is from molecular orbital diagram. Next question is, the fissile carbene metal center is in low or high oxidation state, and in shock carbene metal center is in low or high oxidation state. So if I explain all the properties of these carbenes, we can directly come to this slide and directly see. Carbon should be electron deficient, stabilized by hetero atom phenyl groups, or attacked by nucleophiles, in which in Fischer carbenes. And metal should be present in low oxidation state, electron rich, okay, attacked by electrophiles, stabilized by electron accepting ligands. And metal carbon, relatively weak bond and low rotational barrier, okay. In shock carbene, electron rich carbon are required, destabilized by hetero groups, attacked by electrophiles, okay. And metal should be present in higher oxidation state like D2, D0, etc. 16 or 14 electron metals are preferred for these type of carbenes, and attacked by nucleophiles, stabilized by electron donating ligands. And metal carbon bond should be relatively strong. Large rotation barrier means the hindrance towards the rotation of bonds. The next question, in spontaneous reaction, dg is delta G. Value should be negative. As I have explained earlier, whenever there will be a delta G negative, the reaction will go spontaneously. Means it do not need energy from outer body. That's why it can go on, and that's why it is called spontaneous reaction. I have already explained this in the doubt clearing session. For Heck coupling reaction, in olefin insertion step, oxidation step of palladium will change state. Oxidation state of palladium will change into palladium 2 to palladium 2. I will show how. If you see here, this is the question. Olefin insertion. Here, olefin insertion is happening, and we can see here the oxidation state of metal have not been changed, because whenever it is coordinating here, this R is directly coming here, and that is why oxidation state remains same. Fine. And this is the mechanism for Heck reaction. I have already explained it, but right now we are going through a revision session, so I will summarize all of my 4 lectures in this session. Fine. So it is predict the outcome of the following intermolecular Heck reaction. We directly know alkene alkyl halide, palladium base. Fine, and directly go to the product. And whenever there is a cross coupling reaction, always prefer for the five membered rings. Fine. So this is our mechanism of this reaction, and this is the answer. Let's move to the next question. Predict the following reaction. Suppose we have here alkene, halides, right? And we have here palladium catalyst. So if we see either bromine or iodine, or maybe both, fine, but bromine and iodine both are prone towards this reaction, so they haven't given the amount of this. So we will be doing for all the centers, means wait, this one and this one. Okay, as I have already told. So initially first will be with this, then these two will be coupled with this molecule, and it is the example of Heck coupling reaction. Fine. The classical Heck coupling reaction involves the palladium catalyzed substitution of either vinylic, arylic, benzylic, aliphatic hydrogen with vinyl, aryl, or benzyl groups. Okay, it is vinyl. Okay, we can see here. The mechanism I have already explained. So now we come from, and I think it is an important reaction in this exam. This can come. Something from this reaction can come. How many equivalents of Grignard reagent is generally used in Klinikowicz reaction? The answer is two equivalents. The first equivalent is used for one insertion of ethylene, and next one is used for a second insertion. Fine. What valence electron count is usually associated with the stability when thinking about transition metal organometallics? So, 18 electron rule is generally used. Fine, generally 18 electron used for predicting the resolution formula, stable metal complex, and all. The rule is based on the fact that valence electron transition metal consists 9 valence orbitals. Fine, 1s orbital, 3p orbital, and 5d orbital, which collectively can do 18 electrons as either bonding or non-bonding. But there is 16 electron rule is also okay. You need to go through this also. Whenever there is square planar type, I think geometry, then it will follow 16 electron rule. Fine. Organotin is used in which coupling reaction? It is directly, we can say, still a C. Tin. Whenever you see tin, it is still a. Whenever you see boron complexes, it is Suzuki. Whenever you see what? For Komoda, what? Do anyone have answer? Answer me in the chat box. This is the question for you. In Komoda, what we use? SN. Lithium. Okay, I think magnesium. Okay, I have written magnesium here. Okay, but I don't think lithium is used. Maybe in new reactions they are using. I don't know, but lithium is something different. Fine, let's move. So here, if we see this and this, is it not similar to the carbonyl? It is negative. It is positive. Fine. Can attack here. See, this is what happening here. Okay, whenever it will attack here, negative charge will here. Whenever it comes back, who is good leaving group? It is a good leaving group. It will leave, and this is the product. Fine. Similarly, this one. See, this is the base. What base can do? Base abstracts proton, so it will abstract proton. Suppose it is abstracting proton from here, right? So what will happen? Negative charge will come here, satisfy the positive charge, double bond. This is the product. Which one of the among following Grubbs first generation catalyst? Okay, fine. For Grubbs catalyst, I have already added one slide where you will get all the Grubbs catalyst. That means first generation, second generation, and Hueda grubs. Okay, here are the advantages, disadvantages I have already summarized, and due to the lack of time, I will not explain it, and I have already explained it in the doubt clearing session. Fine. Predict the outcome of the following reaction. It is a ring closing metathesis. Could you please tell me the product? Anyone? First, second, third, fourth. Okay, he's saying first. Fine. Let's see how it happens. Initially, the metal will come and interact with the bond. Fine. Four-membered ring. The metal is inserted here. Then again four-membered ring formation. This is the product, and then again here the regeneration of the catalyst, and this will form this will participate again here. Okay. Fine. Next. The same ring closing metathesis. Tell me the product. Such questions will come in your exam. Okay. The guy is saying D. The product is D, and this is the mechanism. Similar manner. Okay, and this is the regeneration procedure of this active catalyst. Fine. The alkylation of two terminal olefins accompanied by the release of ethane is defined as. The options are cross metathesis, ring closing, olefination, cycloaddition. Ring closing metathesis. I have already shown you the ring closing metathesis here. One example, two example. Okay, so this is the ring closing metathesis. This is also one example. It can jump up in your exam. Who knows? Fine. Among the following incorrect option about alkene metathesis. Again, this is a question from metathesis. Metal carbene involvement, cyclobutane intermediate, concentrated pathway, metallocyclobutane intermediate. Okay, cyclobutane intermediate. Yeah, it's the right answer because cyclobutane intermediate will not form here. Here always forms a metallocyclobutane intermediate. I have already let me find here. See this intermediate, this intermediate, fine here, and here also this intermediate. Okay, this intermediate. They all are metallocyclobutane intermediate. Fine. So again, now tell me which reaction is this. These are called Simon-Smith reaction, and they are generally used for cyclopropanation. Okay, initially zinc coordinates with the one center, and this type of butterfly transition state forms, and the removal of this catalyst occurs, and it is the formation of new product that is used cyclopropane. Fine. Again here, this cyclopropane formation can be done using carbene in the presence of metal. This is the answer. This is the concerted mechanism for this. The major product from the again see zinc, Simon Smith. Tell me the product. See, seeing this, you can tell one thing. Either this or this will be your product. Okay, fine. So again, the mechanism we have already shown, and this will happen because this is coming anti, because already a bulky group is on the above the plane, so it will attack from below. But such conditions will not happen in the case where the molecules are present, which can coordinate or interact with the zinc. So in such situation, suppose here OH group is there na, then the right answer will be B. Okay, keep in your mind, this question will make you confuse in the exam. Bulky group will be there, but maybe the professor puts their group which can interact with the zinc, then the stereochemistry will change, and you have to decide accordingly. See, this is the same question. It should come from the answer should be this, but the answer is this because here the coordination of OH occurs, and such type of product will form. Okay. So this is another type of cyclopropane formation reaction in the presence of titania and RMGX. And here is the mechanism for this. And for better understanding of the mechanism, you can go here, and it is the Klinovich reaction. Okay. Predict the product again, Klinovich. The product is directly this. Whenever you see RMGX titania in the acidic condition, directly you can tick on the cyclopropane. Fine. Again, now tell me what may be the product with this reaction. RMGX titania product. Phosphine ligands are both sigma donor and pi donor. State whether true or false. Tell me the answer. Okay, false. Right answer. So if we see from molecular orbital diagram, the ligand donates through sigma donation, and pi back donation occurs from filled d orbital of metal to the empty sigma orbital. Okay. Which of the following pathway will not be involved in the Suzuki coupling reactions? Oxidative addition, beta hydride elimination, reductive elimination, transmetallation. What may be the answer? A, B, C, D. Okay, beta hydride elimination. So here reductive elimination occurs, beta hydride doesn't. Okay. Which of the following reactions require a base for coupling? Whenever you talk about base, just think about there is a boron complex. So it is Suzuki. Fine. Okay, if you have a Shonogashira, then also you need base. This is the reaction cycle or catalytic cycle of this Suzuki coupling reaction. Okay. For such questions, you need to directly see if there is a boron complex, if there is a base, if there is a palladium catalyst. Okay, it is Suzuki coupling reaction. You can directly predict and directly form the CC carbon bond and take the answer. So if we say here aryl halide, phenyl halide, or alkyl halide, palladium, a base. I didn't ask for the answer. I was just explaining. Okay, and the product. So if we see here, we need something which have this with the boron, right? Because this base says it can be a Suzuki coupling reaction. Fine. So this is the right answer. Always see people will confuse you with the bases. Remember these bases. Okay. And remember these boron complexes for Suzuki reaction. Fine. Let's move to the next question. It is not pH, it is PD. Catalyst, palladium. Base, alkyl halide. See, it is alkyne, and here we have boron complex. So boron, base, palladium catalyst, Suzuki. Fine. This is an example of Suzuki coupling reaction. Directly tell me the product. He's saying product B. Okay. I have a question. Why not D? You must find the answer. Why not D? So this is the mechanism. boron complex, alkyne. Okay, so this is how organoborane is formed. Then in the presence of this catalyst, aryl halide, the product formation. Fine. It will always get attached. Let me explain why it is not D. It will always get attached at the position of boron complex. So it is trans, that's why the trans product. Okay. Keep in mind. Again, one more example. Now tell me the answer. Which coupling reaction is this? Boron complex, yes. OTF group is a good leaving group. It is kind of halide. This is your catalyst and this is your base. Fine. So it is Suzuki coupling reaction. Fine. So Nagashira coupling reaction is okay. See here base. So this question can be altered. Fine. Directly Suzuki can be changed with the Sonogashira and you will get confused. Amine base. So what? See? No, 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 no. Whenever you are doing Suzuki, Sonogashira coupling reaction, there is copper catalyst, co-catalyst. Copper is co-catalyst to activate the alkyne. Okay, so it will be copper one. Initially, it will be copper one here. Okay, this is the catalytic cycle of Sonogashira coupling reaction, and these are the references. If you are not understanding it properly, you can go through this. Initially, what will happen? Suppose this is our alkyl halide inserted in the metal. It starts from here. Okay, inserted complex. Then here, transmetallation will occur from copper. The alkyne will shift here, and halide will again come to copper. Fine. So here the cross coupling will occur and reductive elimination result in the alkyne formation. Fine. Predict the product for the following reaction. Fine. We have complex, palladium complex, copper iodide. Means it is a Sonogashira coupling reaction. We have base. This is our alkyne here, and this is our alkyl halide or aryl halide. Okay, so this center will be attached with this directly and see the answer will be A. Now the question comes, predict the product from the following reaction. This is again the Sonogashira coupling reaction. Can anyone tell me the answer? Okay. B. Okay, anyone else? Fine, it is B. And tell me why chlorine's not got coupled. दिस क्लोरीन सेंटर वाला जो कार्बन है इनमें कपलिंग क्यों नहीं हुआ? फाइन, आई विल गिव यू द रीजन. This is the reactivity of these alkyl halides towards the Sonogashira coupling reaction. So we can say aryl chloride is the lowest priority. That's why it doesn't occur. Already steric hinders have been enhanced a lot. We can see you can see this review and understand the reason. Pseudocon reaction can be described as 2 plus 2 plus 1 cycloaddition, 2 to cycloaddition, 3 to or 2 plus 1. It is 2 to 1 cycloaddition. Okay. Suppose starts from here and we can see it here. See here 1, 2, 2. Okay. Predict the product from the following. Now see palladium catalyst, iodide, and you can directly jump for the cross coupling. No, no, no. Yeah. carbonyl is there, okay? Carbonyl insertion will occur here, okay, and the product will be this. Whenever you have carbonyl in such situations, initially carbonyl insertion will happen. Keep it in your mind. And this is the reactive mechanism. Here carbonyl insertion will occur, and then this butyl will come, and this is the product. Fine, understand? So here, which catalyst we need, the question is asking. We have alkyl halide, one amine. Okay, so what is happening here? Amine and carbon coupling happening. That means here again, what we have, Buchwald Hartwig have given the concept of coupling of the nitrogens with the alkyl halide or aryl halides in the presence of the solvent and high temperature and base. Okay, so cross coupling reactions occur generally in the presence of palladium. So this is the answer. This is the cycle for the cross coupling reaction of Buchwald-Hartwig. Okay. For better understanding, you can go through this reference. Can you tell me the name of this cross coupling reaction? Predict the product for this reaction. Actually, none of these are the product. First thing. Second thing, can you tell me the name of this? No, no, no. None of the product. None of them is the product here. Okay. Predict the product. Okay. Don't predict the product. Just tell me. Just tell me what is the name of this reaction. See, alkyl halide, nitrogen complex. Okay. What will happen here? Buchwald Hartwig. Okay. Buchwald Hartwig coupling reaction will happen here. Okay. This is your aryl halide and this is your amine. But this will be termed as intramolecular Buchwald Hartwig because it is happening in the one molecule only. Okay. This is amine, this is C, and the coupling reaction will result in a five-membered heteroatomic ring. Okay, this is the product, not B, not C, not A, not D. Okay, now tell me what is the name of this reaction. Do anyone have answer? What is the name of this reaction? Aryl halide, yeah, Kumada. See, magnesium here. So what will happen? This, and this will couple and give you the product. That will be the A product. This one, fine. Sorry. So this is the cycle of Kumada coupling reaction. Further, the given reaction is known as, here we have zinc chloride, aryl halide, fine. In the presence of palladium catalyst, this product have been formed. Can you please tell me the name of this reaction? Fine, the guy is saying Negishi. Yeah, right. It is Negishi. Whenever, okay, now I can summarize, right? If I start from heck, palladium coupling reaction, ठीक है? Suzuki boron complexes. Sonogashira copper iodide should be there, okay? And then if we come for Hartwig, there should be amine. Fine. If I come for the Kumada coupling, there should be magnesium. And if I come for the Negishi, there should be zinc. And for Stille, it will be tin. Fine. So to identify the reaction, you need just one key point. Either amine, zinc, magnesium, tin, copper, or base. Getting my point? Such type of concept will directly give you the answer in the exam. That this reaction is this. Let's move to the next question. The major drawback of Stille coupling reaction. Can anyone tell? The answer is use of tin compounds. They are toxic for humans. Cross coupling reaction must involve which step? In every cross coupling reaction, there is a common step. What is that? Sorry. Okay. What is that? Transmetallation. And this is the reason why transmetallation. In every reaction, I have summarized till yet, there is the occurrence of transmetallation reactions. Okay. Transmetallation will occur in each of the palladium catalyzed cross coupling reactions. With what? Either copper, either zinc or tin or magnesium. Okay. So here I conclude my lecture today. Thank you very much. And your doubts are most welcomed either here or on the doubt clearing session. Sorry, the portal. There is a discussion portal. So either you can communicate your doubts there, or right now I will wait for 5 minutes. See, in the examination, you need to approach the question. And my suggestion is that you read the questions properly and give more importance to the each of the option. Okay, you should use the strategy of eliminating the options. Fine. If you are reading with the conscious of 100 for the question, you should use 150 for the options. The options are the key, and whenever you are using a concept, they will like you will be able to reject options and you will get to the correct answer. So this strategy will help you out through the exams. Suppose there are four options: one, two, three, and four. And you have one concept, one problem, one question here. Read the question properly. Sometimes one word can change the question. Suppose there is a OH group in Simon Smith. In Simon Smith reaction, there is a OH group on the upper plane. Okay, then you will be given getting your propane where? On the upper plane. Why? With the coordination of this OH with the ring. Okay, so such type of questions you need to read carefully. There will be only one key. If you are getting that key, you will get the answer. This is just easy and swift way to understand the problems. Okay. And I do not think that there will be something out from this session. These doubt clearing sessions and this revision session will help you. Kindly post the video of today's session on, yeah. I like, I do not know you have found it or not, but I have already shared all the sessions. Like previous four doubt clearing sessions are there on YouTube. Okay, and I will be sharing this also either today or tomorrow, as video processing takes time na. So maybe tomorrow or maybe today only. It depends on the internet speed, and I hope you will get the link through NPTEL team. Otherwise, you directly can go to the channel of mine and directly you can search it. And okay, tomorrow is exam. Oh, okay, okay. So I will. Okay. You directly go to my YouTube channel. You know na where is my YouTube channel? You can directly search for Shiva Singh, PMRF for my channel. Okay, and you will get it today only. Okay, I will give my best to upload this there. Okay, and fine. I think no doubts are there. and there is no time for the uh, doubt clearing session at the group discussion or discussion session. So this is the final session of ours, and all the best. Do good in the exam. Thank you very much.